All right, everyone. It looks like we're getting folks to trickle back in here. We have a tight session here over the next little bit over an hour, so we're going to get started. Just note, there's been a little bit of reshuffling here, and one of our second to last presentations is being moved up to the front now. So welcome back. We're here with our behavior session, session number 3 of the day. And we're going to kick things off with a presentation by Professor Jerry Wang, from Carnegie Mellon University, who's going to be presenting on behalf of his team for his paper titled Pico-Scale Science for Pedestrian-Scale Solutions, a computational toolbox leveraging molecular simulation for pedestrian dynamics. Jerry, you have 10 minutes, and with about, if you could start going over, I'll come back up here, but until then, the floor is yours.
Well, thank you very much, Professor Flanagan, and thank you all so much for being here. I really am very sorry that I can't be there in person with all of you right now, but what I lack in corporeal presence for all of you, I hope to make up for, at least in some measure, with sharing some fun and exciting ideas as part of this notes paper today. So to kick things off, pedestrian flows are everywhere. This picture back that you see in the background here, this is a picture of crowds and a whole bunch of people at the Hangzhou railway station, not so far away from where all of you are right now. But pedestrian flows are really everywhere, and understanding the behavior of large numbers of interacting pedestrians in all kinds of situations is important just for day-to-day management of indoor and outdoor transportation systems, to evacuations and crowd management stuff. There's really a lot of reasons why we would want to be able to accurately model and quickly model the flows of pedestrians. At large scales, the kinds of dynamics that large pedestrian crowds exhibit can be fascinating and arresting. These are some of the largest human crowds that show up anywhere on the planet during the annual pilgrimage. So this is the circulation around the Kaaba during the Hajj. And if you play this at very, very sped up, about 10 to 50x the real-time speed, you really see these beautiful patterns emerge. So there's a lot of cool stuff to study in pedestrian dynamics. Now, there's numerous existing approaches for numerically simulating pedestrian flows. If you want to very roughly think of these along these 2 axes, making 4 quadrants, this is kind of it's a nice way to think of all the tools that are out there. You've got your continuum tools, which tend to solve partial differential equations that govern the density field for the pedestrians. On the other hand, you've got your particle or agent-based models where you individually resolve the behaviors of individual particles or pedestrians. If you look at all the models that exist right now, another kind of helpful categorization, you've got your relatively less straightforward to interpret ones and your relatively more straightforward to interpret ones. What I really mean when I put these things in quotes is that the ones on the left tend to have a pretty significant data-driven component. The ones on the right tend to have a small number or maybe a modest number of explicitly enumerable parameters that you can write down that typically have pretty straightforward physical interpretations. So there's been a lot of fantastic work in each of these 4 quadrants. The stuff that I want to particularly focus on today, where I think there's a really, really nifty set of opportunities, is in this upper half plane, so particle-based models for pedestrian dynamics, either using some sorts of data-driven interaction models, or, as was done sort of first in the business, these very, very classical interaction models for pedestrians, which have seen a lot of success in reproducing and modeling a lot of pedestrian behaviors, going all the way back to the days of Helbing and Molnar in the mid-90s. So I'm going to give you kind of a rough sense for how these models work, especially these models in that upper right quadrant, which have been used extensively to model a bunch of pedestrian phenomena. These models take the form, they're a set of coupled equations for pedestrian dynamics, and these things go roughly under the name or under the broad umbrella term of social force models. The idea of a social force model, something that is so exciting that even my cat Fred here perks up at the suggestion of a social force model. Social force models look something like the following. So you have some sort of a force rule that gives you the force acting between 2 pedestrians. In most social force models, you have something that I like to call a selfish term. So this is each pedestrian having their own desired velocity and then trying to stick to that velocity, and to the extent that their instantaneous velocity doesn't match that desired velocity, they are going to experience some kind of force. This is self-propulsion to try to get to that velocity. This particular term right here is a proportional controller trying to drive you to that desired velocity. You've got some kind of a random term reflecting the fact that there is a little bit of randomness in pedestrian trajectories, and you have a little bit of a random kick. These things can be calibrated to reproduce the characteristic levels of jitter that you see in real trajectories. And then very importantly, most importantly, this is really the thing that gives the social force model, earns these models the name social force, is that you have some kind of a social force or social interaction in there. So pedestrians experience forces that depend on the spatial configuration of themselves relative to other pedestrians. Most social force models, you can decompose this U into two components, a near field term and a far field term. The near field term tends to incorporate actual physical contact. So you can think of this as the literal brushing of shoulders. When two pedestrians are near contact, they experience some kind of a frictional force. What actually happens when your body brushes up against the body of somebody else on a subway or in a railway station. And then you also have this far field term, which can look like any number of things. In the most original, in the sort of old school work of Kelby and Molnar, this thing looks like some kind of exponential attenuation. So you really try to avoid people who are kind of close to you within a characteristic personal space, D naught, and then far away from that, you don't really care if folks are there. So this is kind of the classic social force model. And if you solve for the forces of a large number of pedestrians interacting through these, and then you use those forces to get velocities and then positions through numerical integration, you are doing what folks have done for a long time, solving these social force models to get pedestrian dynamics. Now, the fun observation that I want to point out here, and this is really the core, the heart of this notes paper, is that models of this general mathematical form, so I have a set of interaction rules for forces, and then I translate those to velocities and then positions, and then I try to analyze all kinds of correlations that come out of these kinematic relations. Models of this general mathematical form are numerically evaluated all the time in the molecular sciences. My research group spends an awful lot of time thinking about a whole bunch of different molecular systems, and some of them are pictured here. But the general form in each of these, whatever these particles are, the general mathematical form is the exact same as this class of social force models that are used to study pedestrian dynamics. Moreover, there are all kinds of specialized and fast software tools that have been developed for such Pico-Scale science. We certainly can't claim credit for developing 99.999% of these, although we've done a little bit in our group as well. There's several codes that just really do the stuff super duper fast. LAMPS is one of them, developed principally at Sandia National Labs. It's an awesome tool for doing molecular/Pico-Scale simulation. These tools tend to be specifically really, really good at strategies for massive parallelization across not just 2 or 4 or 8, but tens, hundreds, thousands, even up to hundreds of thousands of cores in parallel. Both spatial decomposition techniques to handle large systems or many systems or systems of any size. You can break them down to smaller subdomains and evaluate those interactions quickly. They also have techniques for highly parallelized evaluation of long-range interaction terms, which may not decay all that quickly. They're good tools for approximating those interactions. Using these kinds of tools, molecular simulations have been performed with order of 10 to the 10, so billions, tens of billions, or even more interacting particles. The world record now for largest molecular simulation sits in the tens of trillions scale. So these things are really, really very large, although molecular simulationists are always kind of greedy because we always want to get these things out, ideally someday, to maybe even close to the scale of Avogadro's number. So still quite a far cry from tens of billions or trillions. Of course, the interactions between molecules are not social forces. These forces originate from smaller length scale interactions of a variety of forms, very often quantum mechanical interactions. But molecular simulation tools, they're a great starting point. If you want to try to do pedestrian dynamics, I think there's a great case for starting from a molecular simulation tool rather than a pedestrian simulation tool for the following reason. You can leverage all these really, really nice things that have already been developed that are really fast for molecular simulation. And you can also leverage the fact that most of these tools allow you to define user-specified couplings between particles. So this is an example using the Kelby-Molnar social force model. This is some work that we've done simulating bidirectional flow in a corridor. What we've put in here is exactly the social force model that Kelby and Molnar used, but now we're running this within LAMPS, within a molecular simulation environment. Using these kinds of tools, we can produce the same dynamics, the same kinematic data as state-of-the-art particle-based pedestrian dynamic simulators with substantially higher computational efficiency. So what I'm showing here is results of computational throughput measured in number of pedestrians times number of time steps per second of wall time of simulation for a whole bunch of different systems. So we have an evacuation system on the left, we have flow through a bottleneck on the right, and we're comparing these against the state-of-the-art particle-based pedestrian dynamic simulator, JupetSim. And you can see much higher, much faster throughputs, especially in the multi-core case, so that's the orange case, as compared to the green, which is JupetSim. Now you might wonder, and very fairly so, why we need speedy pedestrian dynamic simulators in the first place. And I think there's an awful lot of reasons for this. It's not necessarily the case that we're ever going to get to 10 billion or 10 trillion. I certainly hope not 10 trillion pedestrian simulations. I hope there's never a particular need for that. Nevertheless, there is a good reason to be able to do hundreds or thousands or tens of thousands of pedestrians super quickly. If you want to do design optimization, control, or in any sort of active way, on-the-fly forecasting, or the development of ensemble models, plus uncertainty quantification, it's actually really helpful to be able to do these small simulations, not just in 1 second, but potentially in 10 microseconds. And that's the kind of speed-ups that moving pedestrian dynamics to molecular simulation environments can enable. So, what's left to do? There's a lot that's left to do. This whole thing, I'm super excited about this. I'm excited to share this with all of you, but there's still a whole lot left to do. There are dozens upon dozens of variants of social force models, which sit somewhere on the speed fidelity Pareto front. Some of them are faster to evaluate. Some of them better reproduce or better recapitulate some phenomena that are observed. There are so many variants of these social force models. Some of these involve functional forms that are pretty easily realized in molecular simulation software. We've done a couple, but many are not. There's also plenty of data-driven social force models that, for example, stick a neural network in as part or all of the social interaction. Some of these are easy to move into these environments, some are not. Pedestrian flows tend to have intense particle scale heterogeneity, which is not really how atoms or molecules tend to be. So these are not always a terrific fit for existing parallelization strategies, but there are ways around this. And another challenge is that simple boundaries like hallways or T-junctions or constrictions are relatively simple to create in general, but there's also a need for more realistic boundaries because most indoor spaces don't look like one simple hallway. Most things are a lot more complicated. To this end, we've developed a workflow which we think is kind of fun to play with that can turn indoor maps. For example, this is a Google indoor map of a mall in California. And through a series of operations, we can discretize this so we can make this discretized representation of an indoor map that is fully compatible for use as a boundary condition within all major molecular simulation software. So this takes me to the end of the talk. The bottom line, what I hope to convey today is that there's an exact mathematical correspondence between a popular class of models for pedestrian dynamics and a set of models for molecular simulation. And this similarity opens the door to using molecular simulation tools to do those same social force model driven pedestrian simulations, but much, much faster. And we've developed a bunch of tools that can help do that a little more quickly and a little more efficiently. So this is a matter I'd be very happy to talk about with any of you if you're interested. Otherwise, I'd be very happy to take any questions.
Thank you so much, Jerry. Any questions from the audience?
Good, it is working. So Jesse Codling, University of Michigan. Wondering on kind of the efficacy with clearly with this, you jumped straight into working with these particle force models of the pedestrian flow. And I'm wondering if this same kind of, like trying to find a similar type of problem could be applied with, say, the continuum models, and if there's a benefit to one or the other. I don't know if you have a comment on that.
Yeah. Jesse, you said thank you very much for that question, Jesse. And just to check that I heard the question correctly, you're asking if some version of this could also be applied to the continuum models, this bag of tricks and connections that can be worked out for the particle-based models.
Correct.
So, assuming that I understood the question, heard the question correctly, I think that that's a really interesting question. I'll tell you, in a word, no, I don't think there is as straightforward and serendipitous of an opportunity as there is here. So, the PDEs, typically the continuum-based models, those things are already being solved to the best of my understanding with the exact state of the art PD solvers. So you'll find a good finite element code or a good finite volume code to do that. That's already how folks who study these from the continuum perspective are solving those problems. There's probably not too much more that molecular simulation people can offer on that front. In fact, molecular simulation people tend to shy away from the continuum solvers in the first place because most of us got into this business because we didn't want to be solving Navier-Stokes and Fourier and Euler-Bernoulli and all this stuff using the traditional continuum approaches. We wanted to do something a little bit different. There's probably not something totally shocking or revolutionary that molecular simulation could offer up there. I also say, as a matter of community, the folks who study this from the continuum perspective tend to be applied mathematicians in the first place. So they're already kind of using those computational tools that make pretty good sense for solving PDEs. So it's a great question. In a word, I think the answer is no. But in a broader sense, I'm always in favor of interdisciplinary interaction. So maybe there's something cool there. But I wouldn't hold my breath that there's some real low-hanging fruit there. I wouldn't hold my breath for that.
Thank you so much, Jerry, and thanks for joining us over Zoom.
Well, thank you all so much for having me. I really appreciate it.